And let's take a look at this problem now. All right, so we have a density. It's equal to k times y. When I write down that density, I should define what y is. All right, I'm going to take y to be the distance at any point from the bottom. So that's going to be my distance y. It's a measure of how high we are from the ground. So if I put this on a coordinate system like this, y would really be my y-axis. Okay, so the idea here is I can't do this problem all at once. I can't just take the volume times the density because my density is varying. So I have to cut a small enough slice where within that slice my density is constant. Now because my density varies with y, that means I have to cut a horizontal slice. So if I cut my slice like this, then throughout this thin slice, my density should really be constant. I'll draw the back half of that circle there. And so this represents one slice. And my goal is just to find the mass in my slice. Any questions so far about the slice that I'm cutting here? All right, then my density is given to me, some constant times y. And what are the units here? Well, it says mass per unit volume, so maybe this is grams per cubic meter. If I want to get mass, if I want to get mass, what do I have to multiply by here? Volume. So in this thin little slice, the mass should just be my density times the volume of that slice. In the slice, it's just that product, because in the slice, my density isn't varying. Throughout the entire volume, of course, it is. All right, so now I have this expression, and so I really have to just look at the pieces here. The density is given, it's that k times y, and then I have the volume of this slice. Okay, well, let's label some pieces here. I'm going to call this piece my width. I already have this distance here as L, that's given to me. And then I have some sort of thickness right here. Because I'm measuring this slice as some distance from the bottom y, that thickness is going to be delta y. So that means the volume of this slice is just going to be the width times the length times the thickness. Now this problem's a little bit tricky because there's lots of letters. Right? Too many letters to work with here. All letters, no numbers. So we really want to be careful about which of these letters are constants and which of them are variables. So what about delta here? Is delta a constant or a variable? Variable is changing as y changes. What about W? W is also a variable, right? The width of my slice changes as I go up and down. What about L? L is fixed. L is a constant. That length stays the same. That value L is fixed for this, whichever slice I'm in. Okay, so now we have this. So now, if we go ahead and try to find the total mass, we could take the sum of all our slices to get an approximate value. We would take the limit of the sum to make the exact value. And then we say the limit of the sum is the integral. So all that basically says is that we're going to add these things up continuously. Density W, L, dy. So now what's our goal here? What's our mission at this point? W in terms of y. That's our goal here. All right, so I'm going to draw the front face of this object right here. I'm going to draw that front face of the slice like this. Now y is the distance, the vertical distance to my slice. And I'm going to make a little right triangle here. Here's my little right triangle. Now what are the distances on this right triangle? What is this leg of the triangle? What is that one? Half W. That's 1/2 W. What's this leg right here? R. I think I heard somebody over here say R. This is the radius of our circle. So this is a fixed value of R. And notice wherever I draw that slice, even if I draw it up here, I will get this right triangle, and that distance will still be R. So now I have three legs of a right triangle. I can use Pythag on this thing. I can say that y squared plus 1/2 W, that quantity squared, be careful, it's got to be the quantity squared, should equal R squared. Once again, What are variables? What are constants? Is y a variable or constant? Variable. What about w? Variable. What about r? R is my fixed value. So I'm just going to take this thing, solve it for w, and then I can plug it into here, and then I'll get my integrals in terms of or y, and then I'll be all set. All right, so I just solved this thing for w. This is going to be w squared over 4 equals r squared minus y squared. Then I'm going to get, I'll take the square root, I'll get w over 2 equals the square root of r squared minus y squared. And so w equals 2 times the square root of r squared minus y squared. And then I'm just going to plug all my values in here. I have the integral of my density, which is k times y, times w, which is 2 times the square root of r squared minus y squared, times L times dy. And I'm integrating from where to where? Yep, 0 to r. 0 up to whatever that r value is. And when we're done, we're going to have a formula for this thing, regardless of the size of this shed. All right, we can vary the values of L and R, and we'll just be able to plug it into our end result. So this looks like the integral. Woohoo! Right? It looks pretty ugly, but it turns out to be not too bad. It turns out that density really saves us a little bit. If I get rid of my constants here, k is a constant, 2 is a constant, L is a constant. I pull all these things out, I get 2 times k times L times the integral, 0 to r, of y times the square root of r squared minus y squared. I say, whew, that density saved me. Why did that density save me? Now I can use substitution. I don't do trig substitution. All right, so I'm going to give you a minute to kind of catch up with the problem so far, see if you can finish up this integral, see if we can get some final result value. As I'm walking through, feel free to ask questions about that setup. Make sure you're happy with the setup. No, this is the only way you can set up this problem. I could have done some other things with the equation of a circle. That's complicated. There are other approaches. Now I have to say something loud from the back of the room to really do a good mic test. So. Finish up this integral. See if we can finish up this integral here. Kind of going through the setup. Now we can actually do the separation. So we're going to let, do W substitution or U substitution, whatever you want here. What is your substitution going to be? What is the substitution here? R squared minus Y squared, absolutely. Now remember, this next exam is going to be on 7.5, 7.6, 7.7, and Chapter 8. You're going to need to review the earlier parts of Chapter 7 because you have to do integrals. This integral will be a perfectly valid problem because these sections. So that would be a refresher for those ideas as well as we continue to study for the final. All right, so I'm going to start doing my integration here. So I let my substitution be u equals r squared minus y squared. Why did I use u? Aren't we doing w substitution in this textbook? Yeah, I kind of already defined w to be something else, and I don't want to use two w's that mean different things on the board. I'm just going to use u. U equals r squared minus y squared. I take the derivative with respect to y. I get this value. I solve this thing for dy, and then I plug in my values. So I have my constants. I'm integrating. I leave my y. I take the square root of u. That's where my substitution did. I plug in my value for dy. All my y's cancel out, which makes me pretty happy. Right, and I just simplify the integral from here. I pull out that negative 1/2. It cancels the 2, but gives me the negative sign. Now I'm just integrating this thing. Now I got to be a little bit careful with my notation at this point. Right, I kind of cheated. I went from a definite integral, and now I'm doing an indefinite integral. And I don't like to do that. I think I'm just going to change my limits of integration over. We don't have to do this. We can certainly integrate this and then plug our y's back in. I'm just going to change them on the fly, though. These other limits here where y equals 0 and y equals r. But if y equals 0, what does u equal? R squared. And if y equals r, then what does u equal? 0. So now I'm integrating from r squared to 0. All right, so I have negative k times L. I'm going to do this integration here. I will get u to the 3/2 divided by 3/2, or times 2/3. All evaluated from r squared to 0. Yep. Over 2r. Let's see. Where does the 2r come from? Your derivative over here? Well, r squared is just a constant. Remember, r is just the distance of that front face. It's phi. Whatever that number is, I don't know what it is, but it's just some fixed number. So that r squared is just some number. The derivative of that number is just 0. So that constant piece goes away. That make sense? That's that tricky piece of using these constant values. They're really nice because at the end we're going to have a very generic formula. We're going to be able to plug in R values, plug in L values, and be very powerful to use. But along the way, it's a little bit tricky to deal with some of the notation. Are any other questions here along the way so far? All right, so now I am right here. Now I'm going to plug in some values. I get negative k times L. I'm going to bring out my 2/3. I basically have this thing evaluated at 0, so that's 0 raised to some power, which is 0, minus this thing evaluated r squared. I get r squared raised to the 3/2 power. My negatives are going to cancel out here, which I'm pretty happy to see. I get k times L times 2/3. R squared raised to the 3/2 power is what? R cubed. And that should be my final answer here. And I would clean it up just a little bit. I would put that constant out in front. So 2/3 k times L times r cubed. And a couple things to know. I'm really happy those negatives worked out. Right? Because I would hate to have a negative value for my mass. Yep. You mean going from here to here? Yep. Well, I could have this in front of everything if I wanted, right? I could keep all those constants with each piece, but they would always factor out anyway. I don't know if that makes sense or not. Like I certainly could take this whole expression and evaluate those two spots. I would get negative KL 2/3 0 to the 3/2 power, 3/2 power, minus a negative KL times 2/3 r squared raised to the 3/2 power. I could certainly always write it like that, but whenever there's a constant in front, I can kind of leave that out front and just evaluate the meat of those two limits of integration. If I did this, of course, that would go away. I would still be left with a positive. I would have that same expression. I'm just kind of factoring out ahead of time. Does that make sense? Okay. Other questions? Yep. These two values right here? All right, so along the way on my substitution, I did that trick where instead of doing the integration and then plugging my y's back in, I changed my limits along the way. So if I go up here a little bit, I started it with integrating from y equals 0 to y equals r. I got those right from my diagram. And I'm adding up these slices from this height all the way up to this height, where that height is the radius of that circle. So integrate from 0 to r. But once I switch over, once I do my substitution at this point, getting a little sloppy the more I write on it here. Once I plug in my u values, I have to change my limits over. So I say, when y equals 0, what does u equal? And to make that decision, I go back to my substitution value. So I look at this thing and say, when y equals 0, I plug in y equals 0, I get u equals r squared minus 0 squared. So when y is 0, u is r squared. So that's my new limit of integration. U equals r squared. I do the same thing for the upper limit. Does that answer the question? Okay. Other questions? Yep. Potentially. I mean, you could always do it the other way, but there was that question in the last exam that really did this. And the last exam, we had that question that if you were integrating f of x from a to b, and you made some substitution, they defined the substitution, they said, what are the new limits, essentially? So they had that question to see if you understood that you could do this. And you need to be able to do it both ways. Most of the time, you're going to be able to choose your way. But there are certainly physical applications where you're going to want to change your limits over as you go. Other questions? All right, so what do we got here? 8:30, warm-up completed. All right. That's pretty much the nature of this chapter. These are word problems. They're long problems. There's lots of steps. The game is, can you make it all the way through to the end and get some sort of value? Now we have 2/3 k times L times R cubed, and that represents the total mass of sawdust, I believe, in this shed. So big problems. All right, here's our plan for today. We want to finish up 8.4 by talking about center of mass. There's lots of questions. So we're really going to start this conversation kind of from the beginning of center of mass. I want to start right from the beginning with the discrete case and go through that. And some notes about the upcoming stuff. Basically, Friday and Monday, we're going to talk about section 8.5. Wednesday, we're going to do a review-ish thing. There'll probably be a practice exam sent home either on Friday or on Monday that we're going to talk about in class on Wednesday, which I may or may not be here because I may or may not have jury duty. So just so you know about that. Now, Thursday evening exam 2. So contact me right away if you're going to have some sort of time conflict. If you have some other event, I know there's a production of the Rosé that night, so if you're in that, let me know so we can give you a little bit of early exam. If you have some sort of other Michigan Tech event that's going to have you out of town, make sure you contact me right away. I don't want to be dealing with people on Wednesday evening saying, oh yeah, by the way, I'm going to be out of town. Can I take the exam whenever I want? Right? We have to schedule all our sections, take all these makeup exams, in some room and get the room and reserve all these different things. So let me know as soon as possible. Right? Yep. Same bat time, same bat channel. Right? It's probably too old of a reference for you guys. So, all right. Other questions? All right. All right, so let's look at center of mass. All right. In general, the center of mass is the measure of the middle. It's the balancing point. If this thing was a teeter-totter, it's where the middle is. Right? It's how you balance something. If this was just some metal rod, and I wanted to balance it on my finger, where would I put my finger? In the middle. I put it right there, right? And I'd balance it on my finger, and it would be very impressive. Right? But what happens is I add different weights to different positions along my thin metal rod or whatever this object is. So what if I put, for instance, a 3-gram object, right, this position number 1. Would I still be able to balance this thing if I put my finger at 4? No, I'd have to move it over to the left to compensate a little bit. So if I added some other objects here, 2 kilograms here, 1 kilogram here, oops, gram, not kilogram. And I wanted to balance things with this thing, I had to figure out where do I put my finger. And there's 2 factors that are going to affect where I put my finger here. What are they? Position and the weight, right, or the mass or the weight. Although mass and weight are different things, right, but they're comparable. They're off by a factor, essentially, right? All right, so in this case, if you had to take a guess where I'm going to place my finger, where would it be? Probably 3-ish, somewhere over here. I have to compensate for the extra weight that's on this side, so I have to move over here to balance it. Okay. Now, those are the 2 factors, the mass and the distance, and we're going to combine those 2 things as a product and call it the moment. So there's going to be a moment associated with each of these objects that is the product of the mass and the distance. And what I'm going to do is I'm going to basically take a weighted average of all the moments. So I'm going to take the sum of all the positions times the masses, and I'm going to divide by the total mass. It's going to be a weighted average. And this should give me this average position here. And so what does this actually look like for this problem? Well, my first object has a mass of 3, and it's at position 1 distance away from my far left-hand side. I'm going to add that because it's the sum of all those moments. I'm going to add that to my next object. My next object has a mass of 2, and it's positioned at x equals 2. That's its distance from some reference point. Now what's my last piece? One times 7, right? 1 times 7. 1 gram over position 7. I'm going to divide that by what? 6, right? Sum of the mass. 3 plus 2 plus 1 is 6. I get this value. I just chug it out here. I got 3 plus 4 is 7 plus 7 is 14. I got 14 divided by 6. That looks like it's 2 2/3, or 2 2/6. So 2 1/3. Does that make sense as an answer? This gives me the distance over, 2 1/3, somewhere around there. And it should be off to that side. Yep. It's really just based on some arbitrary reference point. So if I shifted this all over a little bit, all right, there would just be negative values over here. But that final result, it could be negative. It could be some negative distance from wherever you arbitrarily put that 0. So even if you slide the scale, it's still going to work out, as long as it's fixed. As long as you fix it somewhere and work the whole whole problem from that fixed position. This one over here, that's this value right here. That last object is 1 gram over at position 7. Yep. So if I just added some pieces over here, sort of, it depends. In this problem, no. In this problem, no, because this ruler that I'm using is a math ruler, right? Which means it's infinitely skinny and has no weight itself. It's one of those hypothetical lines, right? Now, if this was a real object and it had some sort of weight to it, then yeah, if we added a longer ruler, it would be adding up some sort of mass. But that's a tougher problem, right? I mean, if this thing actually had some weight to it, well, then don't I have to take this piece of the ruler, its weight, times its distance? I absolutely do. And that's going to change this idea from taking a sum to taking an integral. Because if there is some weight to this ruler, I can't just add up these discrete values. I have to account for all the different mass here. But how do I add that up? Well, this position times some distance, and this position times some distance, and this, right? It's a continuous thing. Yep. you really could just add it like that. Absolutely. Right? Yep. All right. So that's exactly our problem. That's exactly our extension here. We set up this idea of the center of mass using that problem. You probably worked in elementary school or middle school where you had the little balance beam, and it's like, where do I put the little weights to balance everything out? And you can add up their weight and their distance. But now we need to extend this to a continuous thing, not just discrete values, but something that's continuous. And what do? I just add things up continuously. My sums essentially turn into integrals. So I'm really integrating some stuff. I'm integrating the distance. And then with respect to the mass, but here I'm going to write it like this. This is how I'm going to write it. It's going to be a little bit different than what's in the book. I'm explaining what this dm really is. I'm really going to come right from what would be a Riemann sum. If I wanted to turn this into the infinitesimal case, I could take a sum of the distance and just look at some little tiny piece of mass like this. Now give me some sort of approximate value, and I would take a limit, and those would both turn into integrals with respect to m. That's essentially what I get over here. Okay. But then what is this delta m thing? Well, let's look at a problem here. Here is a problem. So I have this tube, a cylindrical rod here, and the density of the material that's making up this rod, it's not homogeneous. Homogeneous material has the same density, same composition all the way through. This apparently is more dense on the right-hand side than it is on the left-hand side. The density is a function of distance from the left-hand side. It's a function of x. I'm measuring x from the left over. And that density function is 5 times x, grams per cubic centimeter. Okay? So, you know, if this density was just some sort of constant, and I wanted to find the center of mass, where would it be? Right in the middle, right? It'd be right here, sort of. And really, it wouldn't be there. Really, the center of mass would be right about in here. Now, I'm only going to find the x-coordinate for the center of mass, but in general, it is a three-dimensional thing here. If I have a three-dimensional object, the center of mass is going to be a three-dimensional position. But because of the symmetry of this surface, and because it's only changing its density in the x direction, I'm just going to find that center of mass. Okay? I'm just going to find that coordinate of the center of mass. So I have my formula here. I say, okay, so I have the integral of x times dm. Well, if I cut a little slice here, then the mass in that slice is just going to be the density times the volume of the slice. And this is just like all those other problems I've worked before. It's the same thing. It's just like finding the total mass. In fact, the denominator really is just the total mass. So what is the volume here? Well, it's just pi r squared, because I have a disk cross-section, times the thickness. And my thickness in this case is going to be delta x. That's how I'm measuring this thing. And then I just plug these values in. My density is 5 times x. I have pi. What's r? This time it's just fixed. No matter where I cut my slice, it's always just going to be that value of 2. So now I have pi r squared, that's 2 squared, dx. And I'm integrating that from where to where? 0 to 10. So this is really just an extension of finding the mass of something. And it's really just an extension of that discrete case. It's just a weighted average. It's mass times distance, numerator divided by the total mass. The denominator integral is that whole same thing except without the x in front. It's 5x pi 2 squared, which is 4, dx integrating from 0 to 10. Well, great. I can just pull that x out and cancel those integrals, right? No, don't do that. Right? Be careful. You can't just hack stuff on the top and the bottom. This is an integral on top and an integral on the bottom. We don't have rules for hacking and slashing integral fractions. Right? We don't have those rules, so please don't try to make them up. Now what we can do is we can factor constants outside of integrals and then separate the integrals from those fractions and look at that. So for instance, 4 is a constant, 5 is a constant, pi is a constant. So I can really factor all those things out and call this 20 pi times the integral from 0 to 10 of, looks like I'm left with an x squared inside the integral. In the denominator, I can pull out the 5, I can pull out the pi, I can pull out the 4. I'm going to get 20 pi out front, integral from 0 to 10 of x dx. And now I really can cancel these things out. So I can do some cancellation, but you got to be careful. That stuff's got to be outside of the integral. Okay, I can't take the integral on top and say, oh, x squared divided by x is x. I can't cheat like that. I can only cancel things that are outside of my integral. And now I just chug through this integration. What's the integral on top? X cubed over 3 from 0 to 10. On the bottom, I get x squared over 2 from 0 to 10. This leaves me with 10 cubed over 3 divided by 10 squared over 2. I will get 10 cubed over 3. Instead of dividing by a fraction, I'm going to flip and multiply. Times 2 over 10 squared. I'm left with 110 in the numerator. 10 times 2 is 20. Left with a 3 on the denominator. I'm going to write this as a mixed number just because it will help me see the value a little clearer. All right, this looks like it's going to be 6 2/3. And then whenever we get done with this problem, we got to do that last check. Does this answer make any sense at all? And it does. We expected that if the density was constant, I would balance this thing in the middle. But it's more dense on the right-hand side. Right, there's more mass over there. It's going to be a little heavier on the other side once we factor in the effect of gravity. So if I want to balance it, I got to slide my finger over a little bit. So my center of mass should be to the right of that 5 value. Questions about this problem? Yep. This 5 right here? Which 5? This 5? This is my density piece right here. 5x. Sorry, my 5 looks like S's, right? Sorry about that. 5 and 5 here. Sorry about that. Yep. Sure, so I am right here. Let's do one in between step here. I'll just do it with the top integral. I have the integral from 0 to 10, and I have all this stuff. So I'm just going to group it a little bit. I have x times x, that's an x squared piece. I have 5 times 4 times pi, that should be 20 pi, right, dx. But this stuff is just a constant. Right? So if I'm integrating 2 times x dx, that's the same as the integral of 2 times x dx. Or I can pull constants outside of my integrals. I have that property of integration. So that's all I'm doing here is I'm just saying, okay, I have this constant piece. I'm just going to write that as 20 pi times the integral from 0 to 10 of x squared dx. Is that the question? Okay, good. All right, other questions? Yep. Okay. Question? Absolutely. And in some cases, we can shortcut that. Depending on if it's all constant, we might be able to just look at that whole volume. If everything is constant, it works out perfectly and say, density times volume, that's the mass, hooray. But we might not be able to do that in the numerator because now we have to multiply by x along the way. Okay? So that numerator, you are going to have to integrate. So the denominator sometimes, depending on what's given to us as constants, maybe we can shortcut. Other questions? A lot of good questions. Make sure you ask them if you got them. Does it answer a lot of the questions that I was popping up on that pre-assessment? Does going through this base case help a little bit? Okay. I try not to overlap the video too much, but in this case, it sounded like we needed a little square one start. Okay. All right. So what if the density was just 5 and we did that same exact problem? All right, well, if we did that same exact problem, we would still have our formula. It would still look like the integral of x times dm, the integral of dm, integrating our mass here. And now we would have the integral of x. That little piece of mass was the density times our volume. So density volume. But if our density is just a constant, if it's a constant, these can come out front. Now, if it's not a function, it's just a constant, we can pull those out. If we pull those outside of the integrals, then what happens to them? They just cancel out. So if the density is constant throughout our object, the center of mass should just be the center of mass. It should just be the middle. Okay. So that was the only stress here, is that we can factor some of that stuff out if density is given to us as a constant. All right. I think we'll see that more in examples as we do them. Now, I want to talk about the formulas. Dun, dun, dun. These are the formulas for the book. Ugh. Different than I've written them. And I want to talk about how I'm writing them and how they're writing them and why they're a little bit different. This is how they write them in your text. They say the x-coordinate, the center of mass, is this thing. And the y-coordinate is this totally different thing, but looks kind of similar. But there's these a sub y's of y pieces. Okay. And the idea is, why 3 different formulas? All right, well, I'm going to draw some sort of make-believe volume on here, not caring too much about what I draw. Now, if I want to find the real center of mass for this volume, I basically have to do this process that I just did 3 times, 1 in each direction. I have to add things up like this in the z direction to find the z center of mass. I have to slice it like this and add them up in the y direction to find the y center of mass. And I have to do that in the x direction to find the x center of mass. I have to do that each time, in each direction. But in each case, what I'm going to do is I'm going to cut a slice, for instance, this slice, right, like that. I'm going to say, what is the mass in that slice? And the mass is going to be the density times the volume of that slice. But the volume is just going to be the area of the face times the thickness. And if I'm finding the z center of mass, I'll be integrating with respect to the z direction. Right? So my mass piece will always look like this. The area might be different depending on the actual volume that I'm working with, but it will always look like this. So really, when I do any of these center of mass things, when I do this, I'm just doing this. I'm saying, okay, x times dm integral dm. And when I do y, I'm just doing y dm integral dm. But when I look to find that little slice of the mass, that little piece of mass, it's going to be the mass in my cross-section. And the cross-sections I cut are going to be different if I'm trying to find the x-coordinate or the y-coordinate. So all they're doing with their formulas is saying that area piece, well, that's going to be different depending on how you slice it. And so they're giving them different names in each case. Right? So that's the only difference. But this is really the core. The core is just really integrating your distance times that piece of mass and dividing by the total mass. Yep. Yes. Right. Yeah, once you find the mass, it applies to all 3 problems. Mass is going to change depending on how we slice it, right? Other question? Yep. Right. I mean, it will be a function, right? Because if you think of this slice, that area for this one, it's my A, in this case, sub z of z, is this area right here. But as I continue to slice, now my area is different. It's a little bit bigger. It's a function of z. Right? So as I add up all those slices, that area piece changes. Okay? So all this piece is, this area times dc, is really your dv piece. It's just the volume of your slice. So it all comes back to that picture of cutting the slices and adding up all your slices. The formula looks a little ugly, but if you just cut the slices and look at the slices individually, all these pieces just fit in. All right, that's a lot of talking. Let's do an example problem. All right, these ones are a little formula-ish. So you know what? I'm actually going to skip this given our time and jump right down to this thing. Find the center of mass of this thin metal plate. So this is like the surface of a thin metal plate. And I want to balance this plate on my finger because I think that's really cool. Right? So the question is, where do I put my finger on this thin metal plate to balance it? I have to find the x center of mass and the y center of mass. So I'm going to do the x one first. And I'm just going to write out my formula. X times that little slice of mass and total mass on the bottom. And I'm going to draw my slice. And this is why that general approach works pretty good here, because in this case, I don't really have delta times some area and some distance. Because really here, my slice is just going to be an area. And my density is kilograms per area. So if I look at the mass of my slice, what is it? What is the mass in this little slice? What is it? X squared times x. How did you get that? Yep, so I'm going to need the height here, right? And you're right, that is absolutely x squared. And what's the thickness? Dx, absolutely. And if I multiply those together, I'm going to get an area. And I want that area because to find the mass, I'm going to take the density, which is mass divided by area, and I want to times it by an area. So I'm going to go through this little intermediate step, which you don't have to show if you don't want to. But I say, oh, now I'm just looking for the area of the slice. Now it's just density times height times thickness. So I really encourage you to write those in between steps. So you don't have to show your work, write this little piece in here, but I think it's very instructive. I think it will help you and guide you along your way. So that's it. That is my little slice of mass. So I'm going to plug in my values here. X times delta x squared dx. And the integral in the denominator is just going to be delta x squared dx. Integrating from, looks like 0 to 1 in this case. I can put in my values of 5 for my density, but it really doesn't matter because those 5s will just come outside of the integral and they will cancel each other out. And then I'll just go through this integration. Any questions about this one? I'm not actually going to go through the legwork here. But I encourage you to do it because you'll get a number and then you can ask yourself if that number makes sense or not. Any questions about this first piece? But that just gives me the right center of mass in that direction. It doesn't actually tell me where I want to put my finger. To do that, I got to find out what the y center of mass is. And to do that, I use my very similar formula. Y dm, integral of dm. But this dm is a little bit different because now I'm not cutting my slice this way anymore. Now I'm cutting my slice this way. And so now I have a new slice. So now I say, what is the slice in this? Or what is the mass in this slice? Well, once again, it's density times area, just like it was before. But once again, this is why your formulas in the book say A sub y of y. Because now we're slicing in a different way. So this delta A is different than the last delta A. It's the area of this slice, not the last slice. And so if I want to find this, I'm going to need this distance times the thickness. This distance is going to be 1 minus the square root of y. So this is density times 1 minus the square root of y times delta y. Where did I get that 1 minus the square root of y? That's that same area problem that we worked on in 8.1 and 8.2. I have to solve my function. That's really y equals x squared. I have to solve it for the other variable to find this distance. And then I'm just taking 1 minus that distance to get the width of my slice. So now I have a new expression for delta m. And I chug everything in here. Y times delta 1 minus the square root of y dy. And once again, if I have this number value, I can just write in that number value. Or because I want to practice integration, and I just love to integrate things, I can do this one as well. And then I have to be careful with my limits here. This also turns out to be 0, 1, but it's a different 0 to 1. All right, this is y equals 0 to y equals 1, where this was x equals 0, x equals 1. Coincidence in this case. Questions? Finish up this problem at home. Finish up these two integrals. Get your number values. They should be over here somewhere, right? When you think of this plate, where would you naturally put your finger to balance it? Somewhere in this middle piece. So you should have a value bigger than 1/2 and less than y equals 1/2. Okay? So finish the problem on your own, and we will start with another kind of practice problem, and then we're going to get into 8.5. So make sure you prep for 8.5. And office hours are right now. And Faith, can I have your exam here? Yeah, wait till you see 8.5.